Awesome. Thanks so much, Devin. We're going to pass that along now to Paul, who's going to talk to us about cave radio locations. So go ahead and share your screen, Paul. And if everyone else could turn off your videos just for the lack of distractions, go ahead and take it away, Paul.
All right, I've done cave radios for a really long time, and let's see, that's not allowing me to actually go ahead. There we go. One of the things that we do with the cave radios is a thing called a location beacon, and some of you have seen some presentations on this before, but there's a lot of new people, and I thought I would try to do a little bit of update on this. The cave beacon creates a magnetic field around the antenna, which can be detected remotely on the surface. We level the transmitting antenna. It has a null directly above its position when we do so. The current beacon system that I'm using now works at audio frequencies, 3495 hertz. So here's a graphic that shows what the cave beacon magnetic field looks like centered on the antenna. So we have a depth that the antenna is at somewhere below the ground. And then we have an offset where we can actually measure what the field does for us. And then right in the middle, we find ground zero if the underground antenna is leveled perfectly. Here's another better graphic, I think, that shows how these lines of flux, or these field lines, actually are generated. This particular antenna that was in this graphic was a vertical antenna. All the ones that I use are horizontal antennas, so we use a bubble level to level them. There is a way to make a vertical antenna where you could support it from a string or something like that. So to use the loop antenna on the surface to find the direction to that ground zero null, we look at different positions, which gives different lines which converge at ground zero. So we rotate the antenna, and we will hear the sound, and then we get to a place where at a certain angle of using that antenna, we come to this null or no signal. When we're at that part, we know that the receiving antenna on the surface is basically 90 degrees to the transmitting antenna. So somewhere along the line of the receiving antenna is where the transmitting antenna is. We don't know exactly where yet because we have to do another thing. So we converge upon it. We take a point as we move around, and we'll go from one point to another point to another point, and we're drawing lines. And I use surveyor string a lot until we find out where those lines converge. So the receiving antenna down here at the bottom, just above where it says figure 2, is in line with the transmitting antenna, but the transmitting antenna could also be in the other direction, which is why we do more than one line, more than one location, and we draw a line across the strings. Sometimes you can tell because it's allowing you to see a signal strength increase or decrease as you move towards or away. But the string method, the line of position method, is much more reliable. We need to converge on that ground zero until the receiver antenna rotates in any direction with the null. When you get right more than about 10 or 15 feet, you can actually rotate the receiving antenna in any direction, and you'll find that deep null. You're right there at ground zero when you can do that. The magnetic field has a loop shape. It's centered up on the transmitting antenna. Measuring the angle of the field from the distance from ground zero allows you to find an estimate of the depth of the transmitter. So here's again that field is created by the underground antenna, and these lines of flux or lines of force have an angle to them, and that angle is mathematically very well known. And when we take our receiving antenna on the surface and we move it away from the vertical and we start moving it at an angle, we will actually find where those where the null is in the angle direction, and that's some distance away from ground zero. So there's a mathematical formula here that you can plug into your calculator, and you go that approximately, actually, it's if you're at a 45-degree angle, you're at 1.78 times. the rule of thumb is that just call that twice the depth. So the distance from the from ground zero to that 45-degree point is 1.78 times. So it's twice the depth down to the location where the transmitter is. The surface receiver must make certain that the measurement is close to the ground zero when you're starting this. Because if you're on the other side of the loop, because the magnetic field creates a full loop, then you can get a very false indication. And you should be able to note that by the fact that if you knew where ground zero was and you go some distance, you don't want to have the antenna pointed in the wrong direction. So the base of the antenna would be pointed rear towards ground zero. Here's some details of the receiver antenna, one of the ones that I use. It's a 22-inch coil of wire. It's wrapped for stability, and it's contained in a thin plywood housing, so it's fairly structurally sound. And inside the housing there, I've laid out these blocks, and the blocks help hold the loop, which is 2 pounds of magnet wire that's all wound and around on a 22-inch circle. Then it's held down inside there, and then another skin goes up over the top of this, and there's a couple of capacitors inside here as well for tuning. And here it is, all painted up nice and bright orange. It turns out that the first time that I used this, it was not painted, and I was doing a location that was actually close to elk season. And I said, you know, that looks a lot like an elk. I don't want to be looking like an elk walking through the woods, so let's paint it bright orange. The transmitter design that I use is designed by Brian Pease. W1IR is his amateur radio call sign. Brian's done a lot of work on different transmitter designs. There's been transmitter designs for location beacons that have been done just about 100 years. Back in World War I, they had something that was somewhat similar to what we use today. But the new versions are very stable. The newest version is much more robust than one of Brian's older circuits that I found out on a location that I was doing one day. Here is one of the transmitter setups that I have. So we have most of the electronics are in the box here on the left, and it has an on switch. And this one has a plug-in with a thing called an ID-O-matic, which I've set just to make a series of Morse code beeps so that it's easier to actually find the null. If you have a completely solid on signal, it's difficult to tell where that null is. But if you have a signal that's turning on and off, so it has a little bit of off time at the same time that it is doing its usual transmitting, it allows you to be able to find that null a lot more easily than it was if it was just a solid signal. This is another one of my transmitting antennas, and this one was a square loop that was wound, and then I put it on a piece of plywood for stability again, but also lined it up so that I could have my bubble level. And you have to make sure that depending upon how the loop is wound, that you do testing to find where the electrical center of the antenna is. It may not be the actual physical center of the winding, but you have to determine that empirically as you were assembling the system. Brian's receiver is a very complex receiver, but it's also very sensitive. My original simple receiver is very easy to build, or you can buy something that's very simple. It's simply for those of you that read schematics, this is an LM386 audio amplifier, and there's about 4 or 5 other parts on the outside here until you get to the speaker. So the antenna plugs into here. You got a volume control, which oftentimes you leave all the way up, a capacitor to set the gain, a couple of other capacitors here, and one that goes off to the speaker. So it's an extremely simple system. Here's one that I built on a piece of perf board. This is my original circuit, and I've used this on many low depth cave locations. It's got a very low parts count, about $15 in kits if you buy it from various sources. Mine was homebrewed on perf board, It's sensitive enough for 100 to 150 foot depths if you're in a very quiet area. It doesn't have any filtering, so noise can be a problem for this one. And to eliminate the noise in the wideband receiver, a very narrow sensitive audio filter and preamp were added to the basic circuit. I've added a metal box to house the circuits and increase the compactness of all the rest of the circuits. I also put multiple inputs and outputs so I can have different antennas with different connectors, and sometimes I do data collection with this. So here's a look at the filter itself. It's a thing from a company called Soda Beams. They're a company that's over in England. You buy this thing for about $53, $55, depends on how the pound is these days, what the exchange rate is, and then there's some shipping to get here. But the thing to note here is that it'll get down to a 200 hertz bandwidth, which is fairly narrow, and it gets right up to my 3500 hertz. 3495 is where my transmitter actually sits. It has user-defined power, filter settings. You do a program on the thing, and then every other time it starts up, it's perfect. It also has a couple of gain settings, and I set those with a switch. So the new path, instead of just the audio amplifier down here, is I have a preamp that then feeds the filter and then goes to the final amplifier off to the speaker. Here's a look at the filter shape. So you can see that there's a very steep skirt on the filter itself, so it's blocking out all of the other noise here, and we're looking at 20 or 30 decibels of noise attenuation away from where we're actually trying to find the signal, and that's extremely helpful when we're in a noisy location. This is two of my receivers. This one actually has a speaker built onto it. This one does not. You have to use headphones with it all the time. Headphones is preferable when you're dealing with a very weak signal. And this one has a couple of different gain controls on it that I use experimentally. This is the transmit beacon when I'm using the 16-inch antenna and the battery to run it. So the antenna plugs into the radio, and then this one has a beeper that's already built into it. So all you have to do is turn on the beeper, and it will actually do the beeping for you. It does have a steady on signal, which is good for testing, and it has a CW key if you want to try to send messages to the surface. I found it a lot easier to use my voice radios. So here we are. This was the first day I used that receiving loop, and you can see that boy, it's got a really interesting color when you're out there in the woods. And here's another look after it was painted orange, and we're doing a location. Sending the beacons underground, you got to get the team to be able to carry your stuff. So you want to try to make it as light as possible. Some teams are unhappy, and other teams are happy enough to bring it along with you. So in this instance over here, we actually, that's Grand Canyon Caverns, and we set this up with an X marks a spot on the ceiling. We actually drilled that hole that we did the location for, and we broke right into that room. When I'm doing locations, sometimes we're doing multiple locations at a spot, and I will set up a cone or something along the way. And oftentimes, if it's something that needs to be recovered later, we'll put in some metal spikes or something that we could find with a metal detector if it's not an area that is all completely loaded full of other metals. Here is a caver that's going underground with the transmit beacon. This was an entrance that was shown earlier today. However, that antenna did not fit through the space, which was expected, but it was hoped that we could get that one in. Of course, it didn't fit. And so what do? You have the 16-inch antenna, so that one doesn't fit. So you build a 7-inch antenna. And I had to build a special circuit to actually drive this. I'll be working on a more efficient way of doing that, but this was something that I cut out with my laser and used a little plastic wheel glued on the bubble level, and it successfully made it through, and we were able to do a good location. So here's a cave location. The strings didn't show up very well, so I drew some lines here in red on top to show that all of the lines converge, and right there in the middle, we were right at ground zero. And when we spun the receive antenna, we were right at the 0. Going further, what will be the next thing is, besides using just the audio and listening to it, we can use a software to find radio. I have a couple of those things now that will go on all the way down to 1 kilohertz, and that will allow us at 3.5 kilohertz to be able to look at the signal, and we can probably find an even better resolution for where exactly the null is, because we can, as we rotate the antenna, we'll go from a peak like this down to where the noise level is down here, where the null will be. All right, looks like we got 2 minutes left. So how many questions we got?
Thank you, Paul. We had one already in the chat from Matt Bowers. What's the source of the extra noise? But Blaze also jumped in and already answered it as 5G. But by all means, feel free to jump in on that if there's another answer.
Yes, 5G is not the big noise creator for us at this frequency, but the extra noise, the noise increases as you go down in frequency. Almost all of it is atmospheric noise. When we have a very sensitive receiver, we actually are hearing thunderstorms that can be on the other side of the planet. They call them spherics. So you can look for some of the low frequency guys, and they're actually chasing spherics where they can hear thunderstorm static from a long ways away. And some of those things, as they go along a conductive path that's in the ionosphere around the Earth itself, it will actually cause some ringing. And there's some very interesting natural noises you can hear from these frequencies.
Awesome, super cool. Does anyone have any other questions? We have a moment where we could take another question.
Mike Van Note was asking why that particular frequency.
That particular frequency is because it's a very good division ratio from the commonly available crystals that these circuits were first designed with. We have much easier ways to do it now, but the TVs, old TVs, if you remember a tube TV, they had a color burst crystal in them, and that color burst crystal divides down very nicely to a frequency that is 3495.6 hertz or something like that. 3495. That's the frequency we use. We could use a lower frequency if we wanted to go a little bit lower, but the noise does increase. 3500 is at a close to a noise null in this area. 3000, 3030 would be better. It would put us directly between two harmonics of the power line frequency.
Awesome. So since we started a little bit late on yours, we do have time for the other questions that have popped up in the chat. So the first of those is, what is the main use for using these cave radios?
The main use is to be able to determine a spot on the surface that would be of interest. So you could be looking for cracks on the surface that are going to try to get to the underground. You could be trying to see if the passage that you're in underground is related to a sinkhole that might be on the surface. So you may be looking for a second entrance. In the case of Grand Canyon Caverns, we had a completely solid ceiling above us, no cracks, nothing to the surface. And we wanted to actually drill down into the cave so we could put a shaft through there that would allow us to be able to drop a power cable to further the exploration back there. So that's the most important reasons for doing that. The other things that I have done this for is landowner relations. There's an entrance that goes in on somebody's property, and it may go underneath somebody else's property. And if there's an argument about that, then we can do a location and go, this is exactly right here.
Awesome. Okay, so then Ray. Oh, sorry. Yeah, Ray has a question, which is, how does the size of the diameter affect the antenna strength?
Well, the diameter of the transmit antenna gives you more signal. So the signal is actually amps turns squared. So the number of amps that you can put through the antenna and the number of turns that you have on it over a distance gets you the actual signal strength that you get. So basically, a larger antenna with the same amount of power will get you more depth. That 16-inch antenna, I've done locations down to around 300 feet with that below the surface in quiet areas. And in noisy areas, sometimes it's maybe 150 feet. The 7-inch antenna, the small one, because I had a very poor driving circuit that was actually driving that antenna, we were only good to around 30 or 40 feet that we could actually receive with that one. That would probably change with a better circuit. Cave rescue, yes, cave rescue, finding ID spots. That was that first location that I showed with the white antenna before it was painted. We were doing that exact thing. There had been a slip and fall in the back of a cave. A piece of rock broke that was holding a rope, and somebody fell in the cave. We're not damaged at that point. However, it was an extremely painful entrance. If we had to get somebody out, we set some spots in the forest, and we said, if there's somebody damaged and we can't get them through the entrance series, this is where to dig the backhoe.
Awesome. Thanks, Paul. And it looks like Carl has a question. So let's go ahead and do that. And then I'll hand it over to John.
Yeah, thanks a lot, Paul. I heard a story once about someone, a caver, who had walkie-talkies at opposite ends of a cave, and they could not receive each other. But if they took the antennas of the walkie-talkies and pressed them against the wall, they were able to hear each other through the walkie-talkie. Does that make any sense to you? Or
Yes,
can you explain
yeah, it
that?
does. No, that's you're getting to voice radios, and I actually know quite a lot about that too. Yeah, you're actually coupling the signal better. The antennas on those walkie-talkies are horribly inefficient, and actually pushing the signal right into the rock can actually couple it better to the rock itself, depending upon the frequency band. If it's the FRS type radios, the 400 megahertz, 450 megahertz radios, those things are very poor in the cave. They don't go very far at all. But if you have much lower frequencies, you can talk easily down to several hundred feet of depth. I know I've done it.